Nucleophilic substitutions. Organic reactions are broadly classified into the following types. Substitution reactions. In substitution, an atom or group is replaced by another atom or group. For example, Rx, an alkyl halide, when treated with alkali, we get an alcohol ROH plus X minus. So here X is replaced by OH. And in addition reactions are usually given by unsaturated compounds. For example, if we consider addition of, say, bromine to propene. So as a result of addition reaction here, we get a saturated product. We get 1,2-dibromopropane. And elimination reactions. In elimination, two atoms or groups are being removed from the molecule, and as a result of elimination reaction, unsaturated compounds are formed. For example, when, say, CH3, CH2Br, ethyl bromide, when it is treated with alcoholic KOH, when it is heated with alcoholic KOH, a molecule of HBr is eliminated and we get ethene. So here one hydrogen atom from this carbon and one bromine atom, they are leaving as HBr, so we get an unsaturated compound. And in rearrangement reactions, an atom or group changes its position in the molecule. And one of the simplest example for rearrangement, that is urea, formation of urea from ammonium cyanate. So when NH4CnO is heated, that rearranges to form urea. Ammonium cyanate on heating, urea is formed. Substitution reactions are classified into nucleophilic substitution, electrophilic substitution, and free radical substitution. So if substitution reaction is initiated by a nucleophile, it is known as nucleophilic substitution. If it is initiated by an electrophile, it is known as electrophilic substitution. And those substitution reactions initiated by free radicals are known as free radical substitution. For example, when methane is treated with chlorine in presence of light, we get CH3Cl plus HCl, and this reaction is initiated by chlorine radical, so it is known as free radical substitution. In nucleophilic substitution, the substitution reactions are initiated by nucleophiles. For example, when alkyl halide is treated with alkali, alcohols are formed. As an example, if you consider CH3Cl, or in general CH3X, where X can be bromine, chlorine, or iodine. So when this alkyl halide is treated with alkali, we get CH3OH plus X minus. In electrophilic substitution, substitution reactions are initiated by electrophiles. Usually electrophiles are electron deficient species and they attack electron rich centers, and aromatic compounds like benzene undergo substitution by electrophiles. So example, halogenation, sulfonation, nitration, etc. All these are examples for electrophilic substitution. For example, when benzene is treated with halogen in presence of halogen carrier like ferric chloride, halobenzene is formed. So H is replaced by X. And in nitration reaction, when benzene is heated with nitrating mixture, a mixture of concentrated nitric acid and sulfuric acid, we get nitrobenzene. And in aliphatic nucleophilic substitution, alkyl halides, when treated with alkali, X is replaced by OH. We have already seen example. So when CH3X is treated with OH minus, we get CH3OH plus X minus. And this nucleophilic substitution reactions, depending upon the mechanism, there are two types. One is substitution nucleophilic bimolecular, in which rate of the reaction is proportional to product of concentration of alkyl halide as well as nucleophile. Whereas in SN1, that is substitution nucleophilic unimolecular, rate of the reaction is proportional to concentration of alkyl halide only. And in SN1 reaction, usually such reactions are given by tertiary alkyl halides. For example, when tertiary butyl bromide is treated with aqueous alkali, tertiary butyl alcohol is formed. So tertiary butyl bromide, when it is treated with OH minus, we get CH3 thrice COH, that is tertiary butyl alcohol, plus Br minus. And it is seen that in this reaction, experiments show that a rate of the reaction is proportional to concentration of tertiary butyl bromide only. Therefore, it is known as SN1 mechanism. And SN1 mechanism, it's a two-step process that involves initial ionization of alkyl halide to form a carbocation intermediate, which is followed by nucleophilic attack. And the formation of carbocation is the slow and rate determining step. And carbocation, it is planar with sp2 hybridization. So the nucleophile can approach the carbocation from either side. As a result, SN1 reaction is accompanied by racemization of the product. So tertiary butyl bromide in the slow step that ionizes to form the carbocation. It is tertiary butyl cation. And in the fast step, this cation is being attacked by the nucleophile OH minus, and we get tertiary butyl alcohol as the final product. So the first step, that is low ionization of tertiary butyl bromide to form tertiary butyl cation. In this step, there is only the alkyl halide tertiary butyl bromide involved. So it is the slow and rate determining step. And here, as there is only tertiary butyl bromide involved, it is SN1. And usually SN1 reaction is associated with carbocation intermediate, and we get racemized product if you start with an optically active substrate. For example, if you start with an optically active alkyl halide, we get racemic alcohol as the product. This is because as a result of expulsion of the nucleophile, we get a planar carbocation. There is equal probability of approach of the nucleophile from both sides. As a result, there is equal probability of formation of product having inverted configuration as well as retarded configuration. And since there is equal probability, that leads to equimolar mixture of both optical isomers, and that leads to racemization. SN2 reactions. Consider the alkaline hydrolysis of methyl chloride to give methanol. So here, methyl chloride, when treated with aqueous alkali, Cl is being replaced by OH, and we get methanol as the product. Here, rate of the reaction is found to be proportional to the concentration of methyl chloride as well as concentration of OH minus. So this reaction is bimolecular. So the mechanism is known as substitution nucleophilic bimolecular. And SN2 reaction, the process takes place through a concerted mechanism. That means the bond breaking and bond formation takes place simultaneously with the formation of a transition state. Unlike SN1 reaction, there is no intermediate formed in SN2 reaction. And there is more probability of the attack of nucleophile from the opposite side of the leaving group. So on the same side of the leaving group, there is less probability of attack of the nucleophile. As a result, there is higher probability of formation of inverted product as a result of SN2 mechanism. We write a simple example. So OH minus plus CH3 Br. First step is formation of a transition state. That means OH minus, the nucleophile, begins to make a bond with the carbon atom of alkyl halide. As a result, its charge decreases, becomes partial negative charge. At the same time, the CBr bond weakens and bromine gets a partial negative charge. So the negative charge is spread over these atoms, and this is the transition state. And initially the carbon atom is in sp3 hybridization, and that sp3 carbon now gets changed to sp2 in the transition state, and this transition state then gets changed to the product, that is OH CH3, that is methanol plus Br minus. Usually primary alkyl halides undergo substitution by SN2 mechanism. This is because the transition state will be less crowded in the case of primary alkyl halides. And since the nucleophile approaches the substrate from the side opposite to that of the leaving group, there is higher chance of formation of inverted product. That means if you start with a chiral carbon, in this example you can see different alkyl groups are attached to the carbon atom, then that alkyl halide will be a chiral one, and in this case there is the probability of formation of inverted product. So if you start with an R alkyl halide, the product formed will be having S configuration. So SN2 reactions are accompanied by inversion of configuration. The transition state, the carbon atom is in sp2 hybridization, and in the final product that gets changed to sp3. And already we have seen in SN2 reaction there is the possibility of inversion. So if you start with a chiral alkyl halide, inverted product will be formed. And let us have a comparison of SN1 and SN2 mechanism. In SN1, it is substitution nucleophilic unimolecular, because in the rate step there is only alkyl halide involved, whereas SN2, that is bimolecular, because there are two molecules involved in the rate equation. Rate of the reaction is proportional to product of concentration of alkyl halide as well as nucleophile. And SN1 follows first order kinetics, whereas SN2 second order. SN1 reaction, it's a two-step mechanism. First step, that is the slow and rate determining step, involves formation of carbocation intermediate, and in the fast step it is being attacked by nucleophile. Whereas SN2, it's a single step mechanism. In SN1, intermediate is formed, that is carbocation, and in SN2 there is no intermediate. SN1, there is a transition state, there are two transition states, and in SN2 there is only one transition state. It's a concerted mechanism, and in SN1, attack of nucleophile, there is equal probability of nucleophile from both sides. That leads to racemization. If the starting compound is optically active, an equimolar mixture of dextro and levo will be formed, so the product will be optically inactive. And in the case of SN2, there is more probability of backside attack of the nucleophile. As a result, if you start with an optically active alkyl halide, the compound product will be having an inverted configuration. And SN2 reaction is favored by strong nucleophile, whereas SN1 is favored by weak nucleophile. SN1, bond breaking and making not simultaneous, whereas in SN2 the mechanism is concerted. That means bond breaking and making takes place simultaneously. Usually primary alkyl halides undergo substitution by SN2 mechanism, and tertiary alkyl halides undergo substitution by SN1 mechanism. This is because less crowding is preferred for SN2 mechanism, because the transition state will be more crowded in the case of if you start with tertiary alkyl halides. And SN1 mechanism is favored by more polar solvents, and less polar solvents are preferred in the case of SN2 mechanism.